Right, so let's continue our data structures class, and today will probably be maybe a little bit harder than usual because we'll be looking at pointers today, right? So that's a plan of attack, and also I guess we'll cover a little bit of abstract classes, things like that. But the main thing is, of course, pointers, right? So things again. You took already the Harvard class, which had the pointers, so no, right? You remember them a little bit, right? No, you have forgotten them, right?
Remember, but bad memories.
Bad memories, yeah, horrible memories, right? Again, I think the issue is, first of all, it's two things at once. One is the memory access, because you're dealing with memory, and it's easy to go wrong, and also because of what I wouldn't say overloading, but some of the concepts, like some of the notation, syntax is a little bit confusing because the star or the star we use for multiplication is also used for pointers, also for declarations and the referencing, right? And also we have the @ symbol, which is used also in different contexts. So we have, again, we don't have enough symbols. We don't have enough symbols in our C++ or on our keyboards, and that's why the use leads to some confusion, right? We also learn about, hopefully we'll get to new and delete, how to get dynamic memory, right? And maybe we'll do a little pointer arithmetic, right? That's our objective, right? Show deep copies of data. All right. So that's the plan of attack. So pointer variable basically is, of course, the content is memory, right? So how much space is needed, right? If on a modern computer, so question might be how much space should be needed for this pointer variable? How many bytes? What do you think?
It depends on the size of the
yes.
heap.
No. But what kind of OS are we using? What are we using? Like, what kind of systems are we using?
64
bits. So 64 bits, how many bytes then?
8.
8, yes, correct. So we need 8 bytes. This is one of the reasons why moving from 32 bits, some people were very notable people are saying, okay, this is going to double the usage, right? If you're using pointers, right? You instantly double the memory usage for all the pointers because you need twice much memory to store the memory address, right? No, because technically, obviously, we don't need the full 8 bytes, right? Because the memory that's too much space. But of course, due to memory alignment, we are using actually all 8 bytes, right? So we can't really have smaller pointers, on a 64-bit system, right? So how do we do it, right? So we get to the star, right? So data type, identifier, and this says this is going to be used to store memory addresses, not data, but actual addresses where the memory is stored. And the thing is, look at this slide here. These three are equivalent, but functionally nobody writes this one, right? Nobody writes this one because, well, that's why we use this one. Why? Because to indicate that this is a pointer, right? Or technically, some argue this could be more make sense. This actually, of course, doesn't make sense, but it's still legal, right? But this is how we usually write. And again, the reason why this first approach is used, we'll see this in the next slide. So what's the issue? This is the issue, right? You could write this, right? And this can lead to errors because you actually you have two variables here. You have a pointer, right? You're declaring a pointer and you're declaring an integer, right? And they are not, they are two different things, right? Integer could be, well, I don't know, could be 64-bit, 32-bit, but again, the address storing is going to be 64 bits, right? On a normal OS these days, right? And so, to avoid confusion, this is what you use, right? So for each pointer you need to start. Obviously, this confusion goes away if we only use one declaration per statement, right? Each row gets one, but of course we're lazy, right? We don't want to just declare one variable at a time, right? So you use this syntax. So star, or how should we say it? Yeah, star, right? We attach to the variable name, and that way it's less confusion, right? But the confusion is not over. Because first of all, let's do some. Let's go to our repository, right? And let me open up a code space, catalyst space fork, right? And let's see some pointers. Let's see. Hopefully, GitHub works today. I mean, it worked before for Python, but I wonder if it's going to work for C++. It should work, right? Setting up the remote connection. All right. Looks like terminal is up. Well, not yet. Well, it's loading. Let it load for a while. Right, we're recording. Right, on. So we go to next slide. Right. So how do we get the memory in? Right. We use the at or address of operator. Right. You know the symbol, right? It's basically when you do this, the pointer, assuming it matches, so integer x. Of course, the question is now, in this, I mean, this is legal. Well, the pointer, right, is actually, this pointer is completely fine. Here, pointer is fine, but what's not fine in this issue, this is a small example, what's not fine? Well, what's the issue here, right? So this part here is completely legal, normal code, but what's missing here? Well, I declared integer, I declared a pointer to integer, my pointer has the address of integer. That seems okay, right? That's part of today's lecture, but what's missing is, I mean, there's missing one line, right? At least one line, right? What's missing? Well, yeah, I mean, x is not, we have no idea what x is, right? X could be anything, could be 0, but it could be, you know, 5,065, I don't know what, right? Because there's no, I mean, we just took some memory address, right? I mean, we just, okay, we have the memory address, but we don't know what's inside, right? So, but again, but it's legal, right? Of course, a good compiler, if you assign some linter, maybe it will complain that you're doing some things which are not a little bit too dangerous. So let's do this code, structures. No, let's not skip. Do we have some, let's do some, we have to start Windows. All right, I guess we can start the copilot. All right, so we get the address, and now of course, so we can get the address, and what else can we do? Well, we have a pointer, right? But usually pointers, okay, so we have the memory address. We also probably want to do what? We want to get the data behind it, right? We have the address, we want to get the data out. So what we use a dot. So this is where the issue is, right? When you declare it, it's a pointer. So this, when you see this type of syntax, right? Somewhere in actual usage, right? We are saying, okay, whatever memory holds, this, okay, assuming this pointer is integer, right? So this means it will take the memory exactly what's stored, you know, for an integer, enough memory for an integer, right? So it could be 32-bit integer, it could be 64-bit integer, it could be something even longer, right? But it will take from that memory address, it will count the bytes, sufficient bytes, and make up an integer out of those bytes, basically, right? So what's interesting, of course, is you could have also, let's say, a pointer or character. So, of course, in that case, you will get probably the first byte, right? You have short integer, you'll get first 2 bytes, possibly, right? And so on, right? So, let's see this in action. Hopefully okay, now we are good. So let's do actual pointers. Pointers, right? Not be confused with pointer sisters. So pointer brothers, right? So let's explore some pointers. Right, first, right. We will, yeah. So here's a simple example. Right, so here we declare uninitialize a variable, right? And here we declare a pointer to integer and assign the address to it. So, right. So let's see this memory, which is memory address of A, right? A, which is a value, right? Integer value. Right, and which is the contents of memory address appropriate for integer, right? So again, right, this thing is what I'm mentioning sort of here. Let's see this simple example, right? Right. So again, so address right? We get the address of array A. So the thing is, what's interesting is, well, where things get really confusing already is we can get the address also of the pointer, right? We can keep going. We can, I mean, everything has an address, right, in the computer program, right? So you can get address of the pointer, and out of that pointer you can get pointer to the pointer to the pointer, right? And again, you can make your programs extremely complicated that way. But we will try not to, we'll avoid doing that as much as possible, right? Again, in general, the trend is don't use too much pointers. Again, I will not try, I probably won't make you use pointers in your midterm, right? In a week, right? Or you, what do you want? No. Okay. Yeah, so for output pointers, right? So let's see this in action, right? Okay, so A is a value, 5, right? Now look at this here. So this is the address, right? So let's count the bytes. 1, 2, 3, 4, 5, 6 actually bytes. You say, okay, what's well, the thing is, of course, actually it's actually 8 bytes, right? But we don't really need all 8 bytes here, actually, right? So, but we do see, of course, this that the contents of memory address is actually, for integer, right? And we get 5, right? So appropriate for integer. So let's see this. Maybe I'll make a slightly more complex example, right? But I said, so let's make a let's store an integer in B, right? Let's say, but we'll use the integer. Let's say B equals, I don't know, 257, right? Now we will create 2 pointers, right? One will be int, one will be char, right? So, right, int pointer and char pointer, right? So, here we are saying, right, address of B, right? So what's going to be value of this? Of course, not going to be 256 again. So what will be value of this pointer? Well, what do you think? Pointer itself, of course, pointer itself will be the same memory address, But the contents when the referencing will be different, right? As pointer as P1, right? So this is a little bit more complex, right? So now let's see this in action. Let's see that. So P1, right? P2, right? Do we need the void pointer? I don't know. I don't think we need to, right? There's such thing as void, meaning pointer which has no value whatsoever. I don't think this is needed. And of course values. There's no values. Values. Value. And value. Okay, so I am thinking it's going to be like, okay, it's going to be 3 or 2 or it's going to be negative, right, car, or what is going to happen here? I don't know, right? Let's see what's inside. Let's see what is the value of this pointer. Okay, so this I think we can skip. Let's see what happens. Okay, compiles. All right, actually print nothing. All right, so 257. Let's do like 200. I don't know, 87 or something like that. No, more. 97. All right, let's do that. Why? Because it's going to be so 297 minus 256, 41, which is what? Okay, yeah. Let's see. AI is correct. I don't know. Right? Let's see. That's correct. Indeed, yes. All right. So you see this, yeah, 41. Right? We printed the value is right. So, but the memory, right? The main point is right. Again, I don't think we need this part here, right? And this means that this would be we cast void, but we don't really need the void. This would work as fine. Let's try this one more time, right? I want to this concept. Yeah. I wonder why it's. Oh, it tries to the reference. Ah, characters. Ah, that's why. Okay, yeah, okay, that's why. All right, Control Z. Yeah, we had this. So, yeah, this thing. Okay, yeah. So apparently the characters actually have the issue. You can just print the actual value. But okay, all right. So that's basic concept, right? So pointers are memory, and again, we see this is 1, 2, 3, 4, 5, 6. Actually, it should be more. Right? Again, 6 bytes. Technically, okay. Let's see the size of the pointers. Let's see the size. Let's see how many bytes each pointer takes. Right? Size of is very important, of course, in C++. Yeah, so okay, like you said, like Edward said in the beginning, it is indeed 8 bytes. It prints out the 6 bytes, right, because full 8 you don't have as much memory, right? So there's looks like there are 2 zeros, but due to alignment, we do need full 8 bytes, right? So we don't really, since again, we are 64-bit system basically, right? No way around it basically for most machines. Of course, if you're embedded machine, you could have even 16-bit. You have 16-bit operating system, right? You'll have your pointer will be only 2 bytes, obviously, because you have memory, only 64 kilobytes, right, of memory, right? So, but here, of course, we can address a huge amount, 18 hextillion or sextillion of memory, which, of course, we don't really need that much. Okay, so this is the basic stuff. Why would you use pointers? Well, if you know the address, right, you don't need to copy everything. You just need a sort of hook. It's like a hook into some data, right? You know where the data starts, right? Or maybe where it ends, right? Usually where it starts, right? You can use it for array access, for pretty much, which actually in C and C++, array access is actually just basically pointer mathematics, actually, right? So things like that. Let's look at some more examples. So the referencing, right? So we see the value, right? Print the value, which we already did here, right? We did here, right? The value. This prints the value, right? This is not multiplication, right? So of course, if you want to multiply, so you probably need that. If you want to multiply this value by something else before, right? 5 times, you need to do something, right? so if we wanted to multiply the value of P1 by 2, we would do this, right? Oh, well, yeah. Multiply 10 by value of P1. We will do this. Yeah, well, that's one way, but that's AI saying do it like this way. But we would do this, or no, that we don't do that, but or 10 times. Yeah, and this looks ugly, right? So we need to do this, right? So this looks ugly. Let's try this ugly way, if this works actually, right? So this is where the confusion starts, right? So, see out value of 10 times value of P1. So it should be like 10 of P1. Yeah, so this should work. Unless I did something. What the heck happened here? See out. There's something missing, or am I completely? What's happening here? Ooh. Where did that come from? How can it? We're using namespace, right? Right. Let's see. Okay, let's compile it. I don't think there should be a problem. No. Or did I misspell something? What's going on?
There's only one semicolon, not semicolon.
Oh, yeah, right. Yeah, very good. You see? Spot the difference. Yeah, of course. Yeah, very good. Very good. Very good. Very good. Yeah, oh, now, yes. So value, 10 times value of P1 is 229 centimeters. So yeah, so this, you see, so here, this is the issue, right? The star serves as two, at least two masters, right? Two contexts, multiplication, right? And also the referencing, right? So, right, so this is okay, so again, remember, we can take any, you know, you have the referencing, right? We can have any value in memory. We have 8, you know, you need 8 bytes of memory somewhere, right? So sometimes it might be useful to have a null pointer. So what's a famous null pointer? Means just, you know, memory 0, basically, right? It's possible. We'll see that, right? But now let's get to some more, a little bit more complex example where pointers could be useful. Is, let's say you have a structure, you have some data. Let's do some students. Let's define some students. I'll just using namespace and say I'm tired of typing all this out, right? Let's declare a student structure, right, with some attributes. What will students have? ID, name, and percentage. I guess a grade or something. I don't know, right? Very fixed, very short name, right? Now, right, this is C type string. Usually we will use AI, but okay, right? So we say it's ID, name, and percentage, right? Structure student, right? So now, let's make them students, right? Yeah, we only saw how many bytes. Let's make a student object, right? You need, of course, initializer, right? Can we do initializer? Student John Doe, or I'll say Alice Brown or something, right? AB, right? Right, Van, ID, right, student S. Alice, I'll do Alice, right? On Bob, student Bob. Bob Green, right? Alice Brown, Bob Green. Okay, Alice has better grades. I don't know what the percentage means, but okay, right. So, but now of course we can get a reference. Now let's pointer to the Alice, and it's very common in C++ if you're doing pointers to actually prepend, right? Oftentimes, especially older code, it is very common to prepend p to the pointer variable name to indicate this pointer. Of course, modern IDEs will show you this pointer, but it's a reminder of older days when, if you don't know what the heck you're working with, right? This was very helpful, right? No, right? So p Alice is a pointer to an object somewhere in memory, right? Pointer, memory address, right? Memory address. Right. And let's do this. Let's do Bob, right? Let's print those addresses, right? Let's print both addresses for now. Right. Address of Alice. All right. So what are they going to be? Yeah, okay. So let's check this out. What's interesting? Okay, so 5860, right? And this is how much Bob is. Bob is 20. Well, is it 20? What do you think? Is it 20 bytes more, or how much? A little trick question. Not 20 actually, right? How many bytes after in memory? Like you have this big memory space, right? There's Alice and there's Bob, right? So how much space Alice has have been given to Alice? Well, no, we don't know actually how much exactly, but at least, right? So Alice starts at 60, Bob starts at 80, right? But it's a little bit of a trick question. So how many bytes are between them? How many? I said 20, but it's not the right answer. How many?
20 times 8?
No. Look at this part here, right? This part here, right? What does that mean? This is, or even here, right? You can see that. What is this? What kind of format is this?
Hex.
It's hex. So what's the answer? Come on, 20. No calculators. Hands off. Come on. 20 in hex is decimal how much? So what's 10 in hex?
Times 60.
No, wait. Okay, what's 10 in hex? If you see 1 0 and it is hexadecimal, what does it mean?
16.
16. So 20 is what?
32.
Yeah, of course. So yes, okay. But let's think. So why did I? Okay. So just a little, just see if you're awake, right? So if you're awake, so let's see this here, right? Why? Let's look at the structure, right? ID. So integer, it probably takes what, 4? Well, to me, I think this is 4 because integers are usually so. This looks like this is actually 4 bytes, right? This is 20 bytes, right? So actually, so space for 19 characters on null terminator, right? On percentage, and we know floats or no, it's actually float is 4 bytes, right? Okay, let's do double, right? Actually, so this is 8 bytes. So this is actually, I don't know exactly which one, like this is actually 8 bytes, right? So we'll see, right? Float is 4 bytes. Not very. Don't use floats. Use doubles, right? Actually, we should be really using doubles. Okay, but okay, all right. Let's do it again. Let's compile it. Let's run it again. Yeah, it's actually funny enough. It's still same memory. It's always going to be no. Okay, keep running it, right? So again, the difference is the same. 32 bytes. So allocation-wise, right? But of course, the address changes, right? You can see it's always 20 hexadecimal or 32. So now let's see this one more thing. What's going to happen when we add? Let's add a char, right? Char grade, right? So 1 byte. So now the question is. So again, another trick question. What do you think will be the difference now between them? Anyone guesses? So 1 byte. We had 32 bytes different, so 32 bytes are allocated. So if I add 1 more byte, so how much would be a difference now? How much? What do you think? What would be a normal person thinking? Remember this C++, but we'll see what the answer is, right? But what would a normal person be thinking? Okay, it's 32 bytes previously, right? So we add 1 character, right, which is 1 byte. So how much should be? Well, that's a good, but again, maybe not that crazy, but okay, but I want the normal person answer, right?
Normal person answer will be 33, but it doesn't work.
Yeah, so, yeah, this is C++ we're talking about, right? So there's an answer. So let's see. Is it going to be 33? It could be, but not necessarily. That's a problem, right? So let's combine. Yeah. Let's see. I didn't allocate. All right, actually. What's what happened here? So structure. Let's enforce. On grade A, or she gets an A, and Bob gets what? That's B, right? B. Okay. You need to allocate those stuff, right? Let's see what happens. Let's make exchange. All right. But it's even worse now. We still get 32. That's even better. Okay, so so what's going on here? What do you think? Why is 32? Why is still 32? Right? Well, it's due to something called memory alignment, basically, right? And memory allocation, right? Especially these days, right? We have all the memory is given in chunks, right? So usually, I think it's power of 4. Right, so 28, 32, right? So, or maybe in 8, actually, power of 8, right? Possibly 24, 32, 40, right? So what's happening here? And again, this is just a wild guess, right? So I think this ID is also 4 bytes, right? So let's add another one, right? So now let's double this. So I'll copy this, Shift Alt arrow, I'll make it double, right? Let's make it double. This is going to copy. So now I'm pretty sure we have 33, right? We know double is 8 bytes, right? Right? Most likely, right? Depends on the system, right? All right, let's see now. So now it should not be 32 more unless I am doing something really wrong. Yep. All right, 7 and A. Yeah, let's do it one more time. Yep, 30. So now it's 48. I added just 4 bytes and I got 48. So it's actually in powers of 16. So it looks like the alignment on this system, on this operating system, is 16 bytes. So we don't get memory right. Again, it does not mean maybe all of Alice is taking up, but it's aligned. Again, when you call it's assigned the memory allocation, happens in chunks of 16. It looks like. It does not necessarily mean that Alice takes up 48 bytes, right? It's just the way the alignment is. So, yeah, this means, of course, there's lots of losses when you actually, all these little in between, like if you're filling out a glass or like something, I don't know, like if you're parking cars, okay, let's do an analogy. Parking cars, right? You don't really get to see all of the space on the street, right? There's some space in between, right? There's some empty space left. Okay. But now that's one lesson. Second part what I want to talk about is, of course, now let's see. Now let's get some data out of Alice, right? So we want to see her percentage, for example, right? So yeah. So this we'll get to this part. We could use pointer dereferencing. Yeah. So this would mean this. So I want to show P Alice, right? So this is one way of doing it, right? Alice ID. This is legal, right? Or let's say her grade, right? So notice this. It's kind of clunky, right? I hope you agree. Right? Above is legal, but very rarely used. Yeah. Instead, we use arrow, which is shorthand for the above, right? So this is the same thing, right? So when you see these arrows, right? So basically, it's shorthand for the referencing of the pointer, basically, right? And then we can use the arrows. So this is very handy. You'll see your C++ is basically full of these arrows, basically, right? So because we're basically constantly dereferencing pointers, right? So here you see these arrows, right? So, but it is basically a shorthand for if you have some structure, right? You have pointer to some structure, and you want to see some attribute, something inside it, right? Then you will see this arrow syntax. So this is one from this part of lecture. This is the main thing I want you to take away from this lecture. And you see ID indeed is 1, right? Because that's her ID, right? So, does this make sense? So yeah, so nobody used this, everybody used this part here. But it is actually that. Alright. Now, what else do we have? Okay, so what do the slides show? They will show you, okay, they show you the same thing, right? I think they show you, right? Yeah, we get the address, we have pointer, yeah, so this is, we could use, right? But this is, like I said, nobody, we don't use this, we use the arrow. We use arrow, right? Yeah. So, syntax, that's a syntax, arrow operator. And of course, you have a pointer to a pointer, you can have multiple arrows sometimes, right? Yeah. So, remember, right, so one of the most big problems, of course, you need to initialize a pointer, right? So, number 0 is the only number that can be directly assigned to a pointer variable. So C++ standard includes null pointer. We can have a null pointer. Let's do a null pointer. Right. Now, null pointer assignment. Yeah. So this is we use this, right? This is actually 0, right? But of course, again, idea is points to nothing, right? So this can, of course, dereferencing. So what would happen if we try to dereference? What do you think will happen? Let's try this. Let's try to break things and explode things. Yes, indeed. Well, okay, even it's in comment. Let's crash it. I wonder what's going to happen, right? Because you're trying to get the value out of nothing, right? Be a nice perpetual money machine or something, right? Get value out of nothing, right? But let's see if it's going to work. It's not going to work, right? It's going to crash. Yes, segmentation fault, core dump, the famous core dump message. This means that we basically try to get value of something which cannot be the reference, right? We cannot, it again, in C, right, you will use 0 here, right? But again, null pointer is defined in a standard since C++, let's see, it's since C++ 11, I think, right? The book says 11, I think it is the case. Reference, right, null pointer, right? It's a standard null pointer, right? Right, so it is usually going to be, you can use, of course, 0 also, right? So again, we can check against it. So basically, it's also considered the who invented null pointer. We can tell you this guy here, C.H. Hoare, right? I think it was null pointer, right? I believe he is the guilty one. Yes, the $1 billion mistake. Yes, this is what he says. In '65, he had this presentation, but basically he called it a $1 billion mistake, right? Or actually $1 trillion mistake, because it leads to many possible errors, right? So well, of course, it's a kind of semi-joke, right? Right. So it was easy to, right? Lot of pain. So lots of pain. So Tony Hoare, of course, he invented quicksort, so he's not completely evil, right? But Tony Hoare, so pointer to nothing, right? Like there's a show about nothing Seinfeld, right? So there's a pointer to nothing, right? So we don't do this, right? So this will crash the program, segmentation fault, right? Of course, since this is not a constant, we would need to assign, we would need some memory. So if, right, something like this, if it's not no pointer, right? And of course, that's common, right, in many languages, these checks, how to make it syntactically nice, like Kotlin, I forget which ones. If you have a null, you reference something which is nothing, right, you don't want to crash, right? So some language offer a nicer way of syntax, right? This will not crash, right? Right. All right. Right. Yeah. All right. Now, let's see. Do we want to take a break or do we have some more material? Let's see. We have some more material. Yeah, we're starting null pointer. Yeah, but I guess dynamic variables we could do in the next section. So I think it's a good start, good stop at the null pointer, and we'll put the dynamic memory next. So again, hopefully the pointers, the referencing, creating of pointers, right? Declaring a pointer, immediately assigning is possible, right? It's possible to just create a pointer here, right? Immediately, right? Right. So that avoids the problem, right? If you immediately say what memory it points at, right? So you say it pointed to Alice. Well, actually points to the memory saved by Alice structure right here, right? Declare it, right? And we can immediately use it. And similarly, we can also use methods. Also will work, right? If you want function methods, if you add something, some sort of helper method, of course we could call it also. All right, but I think that's enough. Let's continue at 12:05. Let's do 12:05.